Hey, this is an introduction to volumes of resolution. I'm just going to do a quick run through what we did in the lesson, along with the second example, the one using parametric equations. So what I need, first of all, is just a quick description. When we come to integrating, what we need to remember is I calculate a y value on a graph at a certain point, and then we sweep that in the x direction by small amounts of x to create tiny areas. Each of these tiny areas get added up to create the area. So we can actually get an area of an equated graph. So the area is the integral from one limit to another limit of the function y that varies with x with respect to x. Now what happens when we come on to volumes of revolution is we start with the same idea. Now we've got an x and a y direction, and this is the value of y, and as I move the value x along, it builds up new values of y, and we can sweep out the area. But what happens if I was to take this line and rotate it about the x-axis? So rotating about the x-axis forms a circle. So what we're now creating by doing this volume of revolution is actually a solid surface like this. So that we've got this sort of, this one's not the apple core, this is sort of almost a jet engine cowling type thing, and each part is made up of a circle going round with the same radius as our y coordinate. So I'll just take a quick copy of that. And what we realise when we put it in is we're now making a shape based upon using circles on the base, and each time we make a circle and we build it up, we've got a circle over the area, and if I make small amounts of increase in the dx direction, this turns into a cylinder. And if we do the area on the base times a direction at right angles to it with a magnitude, we actually have a volume, which is an area times dx, gives us a volume. So our more general form on the end is the volume of this cylinder, of this shape, is the integral of the area as it varies with x with respect to x. Now the area on this one, because it's got a circular cross-section, my area function is pi times the wide amount of x all squared. So to get the area of the circle, we get the radius y, the same y we were talking about here, but we square it to turn it into the radius multiplied by pi. That gives me the area of a small disk. So my volume can actually be written as the integral of pi with respect to x of y, with y that varies with x squared, times pi gives me dx. You can actually use this in different ways to create volumes of other shapes. If we allow the x value to vary directly, you can create a cone. I might make another video showing that. If the area is square on the bottom and it varies with the x, we can actually calculate the volume of a pyramid. And it's this integration of a function that's going to be squaring that gives us the 1/3 you might recognise in those. Okay, so this is how you can actually prove those values. So I said I'd do one of the examples, and the example I said I'd do is the second one, just to take us through the idea. Just a little side note, that is a rotation about the x-axis. It's also possible you may do a volume is the integral of pi x that varies with y squared, and the dy shows you as a rotation about the y-axis. So that's the key notes for this. So let's do an example. And we're doing their example number 5, which is on page 71. We've been given a curve where the x part of the curve is described as 4t squared minus 1. The y part is given by t squared minus t. We need to create an area, or we're going to use the y squared part, but we've been told it's going to be for the area on the x direction where this crosses the x-axis. So we've got our x-axis, our y-axis, and we need to know what value of t gives us these 2 points, so t1, t2, because they're going to be the limits of my integration. So we start off with the y value. I'm going to say the y value equals 0 is t squared minus t, which is t minus 1. That gives me 2 values of t, so t1 is 0 and t2 is 1. So we're going to be talking about creating a volume by rotating this round to create a solid. So the volume is the integral of my y squared times pi from 0 to 1, and that's a function in t. And my problem now is I can't do dy dx because I want to integrate with respect to x. I need to do get this from dt dx, and to get dt dx, remember that we can do it as the reciprocal of dx dt, and that's how we can actually use our functions to create this volume. So I need to know what dx dt is, which is going to be 8t. So we're going to divide by, we'll substitute that. Oh yeah, so we're going to replace dx with dx. Yeah, we'll do it as the replace method. Don't worry about those bits. And we replace dx now by rearranging dx is equal to 8t with respect to t. So I'll put this into my formula, replace everything we've got. So we're going to do the integral of y from 0 to 1 of the function y squared. So that's y all squared times my 8t with respect to t. So there's my dx, and that's y squared. So we got pi integral y squared dx. That's my volume calculation. Let's expand out the function. So we're doing pi for the integral of 0 to 1 of t to the 4 minus 2 lots of t cubed plus t squared, all multiplied by 8t with respect to t. Scroll on a little bit more and expand it. Pi is the integral from 0 to 1 of 8t to the 5 minus 16t to the 4 plus 8t cubed with respect to t. Keep them in brackets, and that evaluates out to pi 8 over 6, t goes up to the power 6, divide by 6, minus 16 t to the 5, so we divide by 5, plus 8 t to the 4, so we're going to divide by 4, from 0 to 1. And stick the values in, so we've got pi. The evaluation when we got t equals 1 is going to be 8 over 6 minus 16 over 5 plus 8 over 4, and we subtract from that the value when it's 0, which makes all of these 0. And when you plug that into your calculator, the final answer comes out as 2/15 pi. And that's how you can calculate the volume of revolution of the parametric equation given here. Okay, that's where we left it. The same basic principle applies to any of them. You do the integral of y squared, and this one happens that I have to change the variable.